let us continue our discussion with Schrodinger's wave equations. In the last class, what we have seen that this de Broglie wave or matter wave resembles with classical wave, and hence Schrodinger developed that wave mechanics in which he incorporated the de Broglie wave into classical wave equations. Today we will use these things and we will derive the Schrodinger's time independent wave equation. Now the general form of a wave motion is given as del square y by del x square is equals to 1 by v square into del square y by del t square. Here, as Schrodinger told that this de Broglie wave resembles the classical wave, here what he did, he only just put this wave function which describes the matter wave that he used in this equation and wrote the equation for a matter wave as del square psi by del x square is equals to 1 by v square into del square psi by del t square, where this psi is nothing but the wave function of the matter wave. Now the solutions to this type of wave equations are in the form of plane waves, which can be written as psi of xt is equals to a e to the power minus e into omega t minus kx. I have written it in the exponential form because all exponential terms can be converted in terms of sine and cosine functions, and sine and cosines are nothing but our waves. So these are the general form of solutions of a wave equation. Now we will do the derivations of these things and we will put back those into this equation and we will derive the Schrodinger wave equation. Now what we have this wave function as psi of xt is equals to a e to the power minus I into omega t minus kx, and this can be written as psi of xt is equals to a e to the power minus I omega t into e to the power minus kx. What I have done, I have just splitted this term into two terms, one in terms of time and the other one in terms of position. And this e to the power I kx, that I have taken as psi of x, and just see the difference between this psi, this is capital psi, this is small psi. This capital psi is a function of x and t, and the spatial component of this wave function I have taken that as psi of x is equals to e to the power I kx. Now substituting this back over here, we can write it down as psi of xt is equals to a psi of x into e to the power minus I omega t, where psi of x is nothing but e to the power I kx. Now this psi of xt is equals to a psi of x e to the power minus I omega t. This psi of x is e to the power I kx. Now if you remember the wave equation, there we had to get the differentiations of this wave function with respect to x and with respect to t. First we will do the differentiation with respect to x. That also we have to do twice because that was a second order differential equation. So here del psi by del x, if you will do the derivation once, then that is, this is a partial derivation if you can see. So here the variable is t, I can take this term out and only I can write del psi by del x is equals to a e to the power minus I omega t into del psi by del x, because this is independent of x, I have taken that out. A is again a constant over here. Now differentiating it once again, I can write del square psi by del x square. This total term is constant, so I have taken this out and this will be derived once more. Now we will do the derivation of this wave function with respect to time. So while taking the derivation with respect to time, this psi of x, which is a function of position will behave like a constant, so we have to take the derivation of e to the power minus I omega t. So a psi I have taken out, only the term remaining inside the derivation is e to the power minus I omega t, and we all know the derivation of e to the power x is equals to e to the power x, but here I can substitute this minus I omega t as some constant y. Now by applying the chain rule, I can write this as del t of e to the power y and del y by del t, that is e to the power minus I omega t will come, then I will have to take del t of what is e minus I omega t, and this is nothing but minus I omega, which I have written over here. So here del psi by del t is equals to a psi minus I omega into e to the power minus I omega t. Now if we derive this once more with respect to t, then here again we have to take the derivative of e to the power minus I omega t, and that will be again the same term, we will get minus I omega into e to the power minus I omega t, and this minus I omega and one more I omega will come from here, that will be equals to minus I omega whole square, and this is e to the power minus I omega t, and what is this? I can write this as I square omega square, and I square is nothing but minus 1, so here we are getting a minus sign over. So del square psi by del t square is equals to minus a omega square psi into e to the power minus I omega t. Till now what we have obtained? We have obtained the second derivative for the wave function with respect to position and with respect to time. We will see the results whatever we have obtained, that is del square psi by del x square is equals to a e to the power minus I omega t into del square psi by del x square, and this psi and this psi are different, this is containing both x and t, and this is only the spatial part of the wave function. And this again with respect to t, what we have done the derivation, that is del square psi by del t square is equals to minus a omega square psi e to the power minus I omega t. And if you remember the wave equation, there it is del square psi by del x square is equals to 1 by v square into del square psi by del t square. Now we will substitute these two values in that equation. This is our general wave equation. We will be putting these values over here and we will see what is happening. So here del square psi by del x square, this value is given over here and is equals to 1 by v square was there earlier. Now this del square psi by del t square is equals to a omega square psi e to the power minus I omega t. Now this a and this a will get cancelled, this e to the power minus I omega t and e to the power minus I omega t will get cancelled from both the sides. After cancelling these terms, I will be left with del square psi by del x square is equals to minus omega square by v square psi of x. So this is the equation we obtained after putting the derivations in the wave equation. Now we all know that omega is equals to 2 pi nu, where omega is the angular velocity and nu is the frequency. And also we know that b is equals to nu lambda, v is the velocity and nu is the frequency. If we substitute these values over here, what we will get? This omega square will be equals to 4 pi square nu square, and this v square will be equals to nu square lambda square. From here this nu square and nu square will get cancelled. After the get cancelled, what we will left with del square psi by del x square is equals to minus 4 pi square by lambda square psi of x. And taking this to the left hand side, I will get del square psi of x by del x square plus 4 pi square by lambda square psi of x is equals to 0. Now we will do some modifications to this equation by considering the conservation of energy. According to conservation of energy, what is the total energy? That is nothing but our kinetic energy plus potential energy. So E is equals to half mv square plus V. This in turn can be written as half mv square is equals to E minus V. Now taking this 2 to the right hand side, one can write mv square is equals to 2 into E minus V. If I will multiply m on both sides of the equation, this can be equals to m square v square is equals to 2m into E minus V. Further, from de Broglie wavelength, what is the value? That is lambda is equals to h by mv. This is what we have obtained in our previous lecture. You can go back and check it. So lambda is equals to h by mv, or mv is equals to h by lambda. If I take this mv to this side and lambda this side, here we have m square v square and mv is nothing but h by lambda. So I can write m square v square as h by lambda whole square. So substituting that back over here, we can write h by lambda whole square is equals to 2m into E minus V. And from here 1 by lambda square will be equals to 2m into E minus V, and this h square will go down, so divided by h square. So this is the equation what we have obtained by substituting the derivations. Now we have obtained one equation for 1 by lambda square, that is 2m into E minus V by h square. So substituting this value back over here, what we will get? We will get this del square psi by del x square will be as it is. 4 pi square was there earlier. 1 by lambda square is nothing but 2m E minus V by h square, and psi of x was there, so that is equals to 0. Here again this 4 into 2, that will be 8. So del square psi by del x square plus 8 pi square m by h square E minus V into psi of x is equals to 0. Now we will do some modifications to this equation. Let us see what is the modification. Do you know what is this h bar? Yes, you are right, that is h by 2 pi. So h bar square will be equal to h square by 4 pi square, and from here I can write 1 by h bar square is equals to 4 pi square by h square. Here you can see there is a term 4 pi square by h square. So this value I can substitute back over here, and I can write this del square psi by del x square plus 2m by h bar square, because this 4 pi square by h square is equals to 1 by h bar square, and 2m E minus B was there earlier, so it is 2m E minus B by h bar square into psi of x, that is equals to 0. And this is nothing but our Schrodinger's one-dimensional time independent wave equation. Because why it is time independent? Here you can see that wave function what we have considered in the beginning, there we had two parts. One is the spatial part, that is e to the power ikx term, and the other one is e to the power minus I omega t, where the t term was coming, but while doing the derivation that automatically went off, and we left with only this psi of x. This is the spatial part of the original wave function. So this equation is an equation in which there is no time dependent term, and that's why it is time independent wave equation. Further, here the position of the wave is described in one dimension. That means the motion is considered in one dimension. Now this is the one dimensional Schrodinger's time independent wave equation. This is a very important question. Generally it comes in your JNTU exam many times, and you will be asked to derive this equation for Schrodinger's time independent wave equation. But here what we have derived, this is for one dimension. Sometimes what happens, you will be asked to extend the same in 3 dimension. Now we will see how to extend this time independent wave equation which is described in 1 dimension. Now we will extend this into 3 dimension. So this is the extension of this 1 dimensional equation into 3 dimension. What I have done, I have just taken this second derivative of the spatial part in all the 3 directions, that is del square psi by del x square plus del square psi by del y square plus del square psi by del z square, and this term will be as it is, and this psi of x is replaced by psi, and here this psi is described in terms of 3 of the coordinates, that is x, y and z. So psi is equals to psi of x, y, z. Now you all know that delta square is equals to del square by del x square plus del square by del y square plus del square by del z square, and this is nothing but our Laplacian operator. Here if we take this psi common from these 3 terms, we left with this Laplacian operator. So this can be written as delta square psi plus 2m by h bar square e minus b psi is equals to 0, and this is our 3-dimensional Schrodinger's time independent wave equation, which is just a 2-step extension from the 1-dimensional things. You don't have to derive anything, just you have to put this and you can obtain the 3-dimensional equation. Hope you enjoyed the derivation of this equation, and as I told, this is a very important concept and you are getting this question very frequently in JNTU exam. So go through this concept very minutely and clearly, because there is nothing to worry for this derivation. Only the thing, first you have to consider the same wave equation as in our classical mechanics. Then you have to consider the wave function as a plane wave. Then take the double derivative for that wave function in terms of x and t and substitute back that into the wave equation. Then you can generate the equation. Hope you will be able to write this in your exam. All the best. We will stop here today. Thank you all. Bye.